We are New Haven Robotics, and we are proud to present our URC 2025 Mars Rover Tenacity.
Our new 6 degree of freedom arm has undergone a major redesign. Each joint makes use of an 80-to-1 strain-wave gearbox, providing less than 3 arc minutes of backlash. We've also transitioned to rectangular tubing for enhanced stability and strength. We have designed 2 specialized end effectors that can be swapped out per mission. The Extreme Delivery Gripper's lead screw actuation and silicone surfaces deliver high levels of clamping force and grip for picking up rocks. The equipment servicing gripper uses a hinging top jaw and a static bottom jaw designed to interface with the various control surfaces on the lander. A linear actuator on the bottom can also be used for typing autonomously or pushing buttons.
The arm is driven with 6 BLDC motors paired with O-drive motor controllers. This year, we have implemented inverse kinematics with a modified Move It 2 servo package in addition to a velocity controller that can be used to control the arm as a backup. Both grippers are open and closed using Dynamixel servos. We have trained a YOLO V8 model to detect the keyboard and are using OpenCV and a lookup table to get the coordinates of the keys, which are then passed to our IK model for autonomous typing.
This year, each system has its own dedicated Raspberry Pi 5, allowing for simultaneous development, greater reliability, and isolation in the event of failure. Each one of our Pis is running ROS 2 on a customized version of Ubuntu 22. Each subsystem has been developed outside of the Rover, allowing subteams to simulate, develop, and deploy their systems onto the Rover at their own pace, which has greatly improved productivity.
Our power distribution unit uses a 48-volt and 24-volt rail to isolate high and low power systems. Each circuit has a fuse and relay for protection and to allow for a remote resetting. Each CPU on the Rover can also be reset individually via the managed PoE network switch.
After having great success with our tank tread design last year, our next iteration has an improved tensioning and suspension system. A set of horizontal springs allow each pair of bottom pulleys to comply freely to uneven ground and large obstacles. Our 3D printed TPU treads now feature taller teeth for increased traction in the sand and reduced vibrations. The treads also feature dual 3 kilowatt motors on each side for redundancy.
Our new science assay uses 2 lead screw-driven augers to ensure our samples are drawn from a depth of 10 centimeters and transported to isolated caches for our 2 life detection systems. Our bioluminescence test uses a luciferin buffer solution, which will bind to the luciferase in the presence of ATP and undergo an oxidization reaction, releasing light, which will be detected through a camera and enhanced with a UV LED. Our pyrolysis test makes use of induction heating to bring our sample up to 500 degrees Celsius and burn off any organic materials present. Our custom GUI allows the operator to control the science assay and monitor all incoming data.
This year's comm system runs on 5.8 GHz, 2.4 GHz, 900 MHz, and 433 MHz bands. The 2.4 GHz and 900 MHz systems are aggregated through our network switch, improving speeds when both bands are in range, while also allowing for a long-range non-line-of-sight link if the main 2.4 GHz signal becomes unstable. The 433 MHz only transmits the necessary messages for basic teleoperation, and, when combined with our 5.8 GHz video transmitters, we can operate the Rover in the event of a near-complete network failure.
We have upgraded our chassis to be more compact and lightweight with an aluminum extrusion frame and custom panels. Our magnetic body panels seal the chassis from dust and dirt with 2 fans for active cooling.
Our team has created a fully custom base station unit with a built-in screen, joysticks, router, battery, and multiple DC outputs, including a 100-watt USB PD in and out. This self-contained base station has nearly 0 setup time and powers our entire comm system on its own, making testing and setup extremely convenient, leading to more testing sessions. The system is easily expanded by plugging a laptop into the network switch, allowing access to the Rover's ROS 2 network. The main camera system uses OIS cameras driven by dedicated RADSA 03E computers, running hardware encoding, Aruco detection, image manipulation, and other features all on board. This system is nearly infinitely expandable, dynamic, and reliable, as the failure of one does not affect the others.
The autonomy of the Rover is powered by a dedicated Jetson Orin NX computer using a Z2i for 3D vision. The individual camera computers are able to detect Aruca markers, providing location data and video streams to the Jetson for object recognition. The user can enter a list of GNSS target coordinates, which are then displayed through MapViz. The operator chooses the order, the Rover then calculates a path and begins its journey.
Based on the type of waypoint, the Rover knows when to begin our custom spiral search algorithm, flash its lights, look for Aruco markers, or other objects of interest. We've developed an in-house navigation and obstacle avoidance system making use of point clouds, differential GNSS, and a multitude of other sensors. Using in-house software ensures we have full control and understanding of the entire system and that it can be specialized for the task at hand.
The team does all the design work in the fall semester for initial prototypes and basic testing taking place. In the spring before the SAR, the team manufactures the Rover and does preliminary testing. After the SAR, there's all testing and final tuning before we depart to Utah.